we have mentioned earlier that the simplest of the 3-phase transformer will have 6 windings and 12 terminals. Whether they are made from 3 single phase transformer or built as a single 3-phase unit, there will be at least 6 windings and 12 terminals. And we have also decided on a terminal convention for them. The HV and LV windings of a particular phase are marked with the same letters. For example, this is called A2, this is A1. Then the same instantaneous polarity terminals on the LV side will be called A2, A1. Capital letter stand for HV winding, small letter stands for LV winding. Similarly, this will be B2, B1, B2, B1, C2, C1, small c2, small c1. Now, there are different types of connections possible with these 12 terminals. For example, the input side can be star connected by connecting the terminals with suffix 1 and the supplying power to the rest of the terminal. Similarly, the low voltage side can also be star connected. This will be high voltage phase A, B, C. This will be low voltage phase A, B and C. We have also seen that in this case the high voltage winding and line voltage phasors will be in phase with the low voltage winding and line voltage phasors respectively. Line currents on the HV and LV side will also be in phase. In fact, the conversion ratio, assuming ideal transformer, will be same between the phase voltage of the two sides and the line voltage of the two sides will be same, and that will be equal to the turns ratio of the windings. However, this situation will change. This is also true if both sides are delta connected. However, this situation will change if, for example, one side is star connected, the other side is delta connected. Let us see what will be the corresponding conversion ratios. So, this is my high voltage side winding. Phase A, is the low voltage winding. This is A2, A1, this is B2, B1, this is C2, C1. Similarly, this terminal is A2, this is A1, this is B2, this is B1, this is C2, this is C1. So, let us say the high voltage side is star connected. So, we form a star connection by shorting the terminals A1, B1 and C1 and giving supply to the remaining terminals. So, this is phase A of the high voltage side, this is phase B of the high voltage side, this is phase C. This is the line current IA flowing and this is the line to line voltage V capital L, and this is the phase voltage V capital P. This is the winding current or phase current I capital P. Similarly, this is the phase current on the LV side I small p, and this is the line current on the LV side I small l. Now, the low voltage side, let us say, is delta connected. How do I get this delta connection? Let us say for that we connect A1 to B2, B1 to C2 and C1 to A2. Still get supply from the terminals A2, B2, C2, which constitute the lines, low voltage lines A, B, C. This is the low voltage line current I small l, and this is the low voltage side line voltage V small l. This is called star delta connection. That is the high voltage side star represented by a capital Y and low voltage side is delta represented by a small letter d. Had the high voltage side been delta connected, it would have been written as capital D small y, delta star connection. Now, let us first try to look at the phasor diagram, the voltage phasor diagram first. Since the basic transformer relation must hold, so this is the phasor, let us say V B2 B1, that is this is the terminal B2, this is B1. This is okay, let us call it A1 A2. This is the phasor C1 C2 and this side is the phasor B1 B2. So, the corresponding winding voltages will be in phase. So, the voltage V A1 A2, this is A1, this is A2. Now, on the secondary side, A1 is connected to terminal B2. So, this will be the phasor B1 B2 and B1 is connected to C2. So, this will be the phasor C2 C1. So, we see that small a voltage small a to A1 is parallel to the voltage V capital A2 A1. So, since these two are coupled to each other, similarly for other phases. So, this is the phasor diagram of a star delta connected 3-phase transformer. Now, let us look at the phase voltage, line voltage, phase current and line current transformation ratio. For that, let us assume that the high voltage side has n number of turns and the low voltage side 1. So, this is a n:1 transformer, in which case we see that on the high voltage side the phase voltage Vp equal to the line voltage Vl by √3. On the other hand, on the low voltage side the phase voltage Vp equal to the line voltage Vl. But from the transformer relation, V capital P is to V small p is equal to n:1. Therefore, V capital L is to V small l equal to √3 V capital P is to V small p. This will be equal to √3 n is to 1. So, the phase voltage ratio is same as the turns ratio, whereas the line voltage ratio is √3 times the turns ratio. Let us look at the currents. So, what will be the current phasor diagram? Again, the currents I capital P and I small p will be in phase in this diagram. So, the current flowing from A2 to A1 will be in phase in the second with the current flowing from A1 to A2 in the LV side in the same phase. So, let us first draw the currents on the primary side, that is the HV side. So, this is, let us say, the phase current IA, this which is same as the line current. This is IB and this is IC. Now, this IA is same as the current flowing through from A2 to A1. So, this will be in phase with the current flowing from A1 to A2. So, the secondary current flowing through phase A1 to A2 will be in phase with this current. So, this is the current I A1 to A2, this is the phase current IA, which will be in phase with this. Similarly, the phase current IB will be in phase with the high voltage current IB. So, this will be the phase current IB and this will be the phase current IC. What will be the line currents? Let us say capital IA phase, IB phase, IC phase. What will be the line current? Let us say line current I small a. This is line current I L of the A phase will be phase current I A P minus this current, which is the phase current I C minus I C P. So, this is I A minus I C P. What will be the I A? This is I C P. So, the phase current I C line the line current I A on the primary on the secondary side will be the vector sum of I this phasor and negative of this phasor, which would be somewhat like this. With this angle being 30 degree. This is I small a. Similarly, it can be shown that the I small b will be 120 degree with respect to this, and I small c will be 120 degree with respect to this. What will be the ratios? Again, if we assume individual transformers to be ideal, then we know n times I capital P equal to 1 times I small p, or I capital P is to I small p equal to n is to equal to 1 is to n. Similarly, for star delta connection, we know the line current I capital L is same as I capital P. On the other hand, line current on the delta side I small l equal to root 3 times I small p. Therefore, I L is to I L equal to I P is to root 3 I small p, and that is equal to 1 is to root 3 n. Again, it should be noted V P I P equal to V small p I small p as well as V L I L equal to V small l I small l. This relation holds irrespective of the transformer connection. This is because we have assumed the transformer to be ideal. Hence, we have seen that if one of the sides of the 3-phase transformer is star connected and the other, the high voltage side is star connected and the low voltage side is delta connected, then in a nutshell we can write the relations for the YD transformers, transformation relation for the YD transformer is V phase is to on the high voltage side to V phase on the low voltage side, this is same as N is to 1. I phase on the high voltage side is to I phase on the low voltage side, this is equal to 1 is to N. V line on the high voltage side is to V line on the low voltage side equal to root 3 N is to 1. I line on the high voltage side is to I line on the low voltage side is 1 is to root 3 N. The similar relation can be written for dy connected transformer. Although star star, delta delta, star delta or delta star are common connections for 3-phase transformers, there is another interesting connection for 3-phase transformer. This is called the zigzag connection. For zigzag connection, one of the sides this is, let us say, the high voltage side of the transformer. A2, A1, B2, B1, C2, C1. On the low voltage side, it is zigzag connected. For zigzag connection, the secondary winding is split into two parts. Each secondary winding, each low voltage winding is split into two parts. This is small a2, a1, this is called a4, a3. This is B2, B1, this is B4, B3, this is C2, C1, this is C4, C3, indicating all the even numbered terminals have same instantaneous polarity and all the odd numbered terminals have the same instantaneous polarity. Now, let us assume that the primary is delta connected with A1 connected to B2, B1 connected to C2 and C1 connected to A2, and the connections are coming from external connections are given to A2, B2 and C2. So, this is phase A, this is phase B, this is phase C of the high voltage side. This is the line to line voltage VL, V capital L. This is the phase voltage Vp. This is the line current, high voltage side line current IL. Let this be the high voltage side phase current IP. Similarly, the low voltage side phase current is I small p. This current I will call I A2 A1, this is I A4 A3, this is I B2 B1, that is from B2 to B1. In order to make a zigzag connection, what is done is one of these sets of windings are star connected. So, one of them let us say A2 B2 C2 is star connected, forming the neutral. The terminal A1, the terminal A1 is connected to B3. And phase B comes out from B4. Similarly, the terminal B1 is connected to C3. And the line C comes from C4. Terminal C1 is connected to A3. And the A phase connection comes out from A4. So, these are the line currents IL. First, let us see how the voltage and current phasor diagrams will look like for this kind of a connection. Taking the voltage VBC to be the reference phasor, this is B terminal, this is C terminal. So, this is basically the voltage of B2 with respect to B1, because B is connected to B2 and C is connected to B1. So, this is the voltage AB this is CA. So, this is BC, this is AB, this is CA. So, here we have actually VBC equal to V B2 B1 VAB equal to V A2 A1 and VCA VC2 C1. Then on the low voltage side, we see that the star point is formed by connecting terminals A2, B2 and C2 together. So, the potential VA1A2 will be in phase opposition to voltage VA2A1, that is voltage VAB. So, this will be the phasor VA2A1. Similarly, the phasor VB1B2 will be in phase opposition to VB2B1, which is VBC. So, this will be the phasor B1B2 and this will be the phasor C1C2. So, this is terminal A1, this is B1, sorry, this is C1 and this is B1. Now, the phase A is obtained by adding the phasor VA4A3 with that of A3 is connected to C1. So, phase A obtained by adding phase A4A3 which is parallel to VAB A2A1 with this phasor. So, this is A3 A4 and my this is the voltage VA, this is the terminal A. Similarly, phase C is obtained by connecting C4 C3 with B1 B2 which is parallel to this. Hence, this will be the voltage phasor VC, or this is the C phase, and phase B is obtained by connecting B4 B3 with A1 A2 and this is phase B. This is what the voltage phasor diagram will look like. Again, we will assume that the turns ratio is N on the high voltage side is to 0.5 is to 0.5. So, since the primary side is delta connected, Vp equal to VL. Also, on the secondary side, let us say V A2 A1 is to V small a2 small a1 equal to 2n is to 1. From this phasor diagram, since A2 A1, the magnitudes of A2 A1 and B3 B4 similar, also V A2 A1 is to V A4 A3 is also 2n is to 1. Therefore, what is the ratio of V A2 A1 is to V A4 A2? V A4 A2 equal to, but from this phasor diagram, V A4 A2 equal to V A4 A3 plus V C1 C2, but the magnitude of V C1 C2 and V C3 C4 are same, and this angle is 120 degree. So, this amplitude is equal to, this is equal to, so mod V A4 A2 equal to root 3 times mod V S4 A3. Therefore, this will be equal to this will be equal to 2n is to root 3, or V phase is to V phase equal to 2n is to root 3. What about the line? The line is simply obtained because on the high voltage side VL equal to Vp, on the low voltage side, since after all this is star connected, this is incidentally called the zigzag star connection. So, on the low voltage side VL equal to root 3 Vp, therefore, we have VL is to VL equal to Vp is to root 3 Vp will be equal to 2n is to 3. One interesting thing to note here is VL is to VL in this case equal to 2n by 3 or equal to n divided by 1.5. For a star connected system, both sides star, there we knew that or if the side was star connected, input side delta connected, output side star connected, in which case we would have seen it differently. For example, for a delta star connection, the Vp equal to VL. On the other hand, on the start side, Vp equal to VL by root 3, but for a delta star connection, Vp is to V small p would have been equal to n is to 1. Therefore, VL is to VL would have been Vp is to root 3 Vp equal to n is to root 3. So, this is the difference. So, suppose I have two transformer, one is delta zigzag star with turns ratio n z. So, VL is to VL, there is n z into is to 1.5. In the other case, I have the same line voltages, but with delta normal star. This is n star by root 3. Now, if in both cases the line voltages on the high voltage and low voltage side are same, then we must have Nz by 1.5 equal to Ny by root 3 or Nz by Ny equal to 1.5 by root 3 or Nz equal to 1.5 by root 3 into Ny. In other words, Nz will be less than Ny, which shows that for the same line voltage ratio, if we use a zigzag star connection on the secondary side, then the number of turns on the HV side can be reduced. So, that gives a cheaper transformer. So, that is why sometimes it is preferred. Now, let us look at the current phasor diagram. The input side is delta connected. So, let us say this is the line current on the high voltage side IA, this is IB and this is IC, IA, IB, IC. From the circuit connection, we have seen that we can write from here that line current IA equal to this current equal to this current plus this current, which is minus of IC. So, it is I A2 A1 minus I C2 C1. Similarly, line current IB equal to I B2 B1 minus I A2 A1 and IC equal to I C2 C1 minus I B2 B1. If we keep these relations in mind, then the phasors I A2 A1 B2 B1 C2 C1 will look like this. This is I A2 A1 this is I B2 B1, this is I C2 C1, with this angle being 30 degree. Now that we have got the winding currents, we can now draw the winding currents on the low voltage side. Now, the currents on the low voltage side, from this phasor diagram we find the current I small a equal to, this is the I small a. The current I small a is basically I A3 A4, which is same as current A3 A4, same as current I C2 C1. Now, it has to be seen that in order to balance MMF, we must have n times I A2 A1 plus 0.5 times I A2 A1 plus 0.5 times I A4 A3, this must be equal to 0. But from the phasor diagram we have seen that I A2 A1 what is I A2 A1? I A2 A1 is this current flowing through this terminal, through this and coming out. So, this is equal to IB. Similarly, I A4 A3, this we have already seen, this is equal to minus IA. So, we can write n times I A2 A1 equal to 0.5 IA minus IB, or n times I capital P equal to root 3 by 2 times I small p, because IA and IB are the phase currents of the low voltage side which are 120 degree apart. So, IA minus IB is root 3 times the phase current. Hence, we have IP is to IP equal to root 3 by 2n. But on the high voltage side, IL equal to root 3 IP, and on the low voltage side, IL equal to IP. Therefore, we have IL is to small IL equal to 3 by 2n. So, this for the delta zigzag star, therefore, we can summarize it as Vp is to V phase equal to Vp is to V phase equal to 2n is to root 3, VL is to VL equal to 2n is to 3e, IP is to IP equal to root 3 by 2n, and IL is to IL equal to 3 by 2n. Again here also we see Vp IP equal to Vp IP and VL IL equal to VL IL, which is due to the fact that we have assumed all transformers to be ideal.